Hello everyone, let me introduce myself. My name is Eric Sabino de Oliveira, recently graduated mechanical engineer from Cefet, and this paper was developed in pair with José Luiz Zanon Zotin, professor at Cefet, in order to investigate the natural ventilation process enhanced by solar chimneys in Rio de Janeiro and Seropédica cities. About the motivations to work on this project, it is known that an important step in home building deals with the internal air circulation due to the importance to remove pollutants and reduce the thermal load. And sometimes other passive ventilation techniques do not achieve good results. So our objective is to check the feasibility of solar chimneys as an alternative method for ventilation. But what are solar chimneys? For instance, here we have two examples of real solar chimneys, but in general they are an open duct that provides the airflow when hitting one of the ends. They can be built in several shapes and have several purposes, either for ventilation, drying, or power generation. In this work, the chimney has a rectangular geometry with an inlet and outlet area equals to a quarter square meters and 4 meters high. The front face is made of glass and the back face is made of high absorbance material attached to an insulation. And this chamber will be heating the air inside of the solar chimney. The consequence of heating the air is a pressure reduction, inducing the air to flow by the room to the solar chimney. In other words, we'll create an airflow between a zone with lower temperature and higher pressure and the chimney zone with higher temperature and lower pressure. The main goal of this work is to check if the airflow created by the chimney is high enough to perform the air ventilation of a room and the best inclination for Rio de Janeiro and Seropédica cities. To achieve this, the first thing done was the data collection at the ENCIT, the National Meteorological of Brazil, where we could access for free the hourly measurements from his weather stations, getting some important information, such as solar radiation, relative air humidity, temperature, atmospheric pressure, and speed wind. Once the available radiation data relates to the solar energy on a horizontal surface, we have estimated how much energy will be received by the chimney on 9 different inclinations, varying them between 10 and 90 degrees. And for last, we perform the energy balance on the solar chimney and solve these equations in order to calculate the temperature of the air, the glass, and the absorber plate, as also the mass flow rate over the system. About the problem formulation and solution methodology, we could start setting up the energy balance for the whole system with these considerations. The glass on the front side receives the solar energy S1, and part of this energy goes to the absorber plate by radiation, and both glass and absorber will be heating the air in the channel. On the glass, we consider that some energy will be lost by reflection to the sky and by convection due to the external wind. The absorber plate is joined to an insulation and there is a small energy loss through it. Using this background, we did the energy balancing in 3 separate blocks, the glass, the absorber, and the inside air, and then tried to solve the system of equations considering each measurement of the database. Due to the time limitation, it's not possible to show all equations, but the relevant ones are shown below. Inside the energy balance, we calculate the mass flow using this equation, and after the iteration process, the thermal efficiency was calculated using this another one. And the Nusselt numbers takes into account the Grashof and Prandtl numbers, where the criteria to set the flow as laminar or turbulent is relative to the chimney inclination. And now we have some of the equations for the thermal properties of the air. The density as a function of temperature and relative air humidity, the specific heat capacity, viscosity, and thermal conductivity, always depending on the temperature. Turning now to the data acquisition, we have chosen 5 weather stations to collect data, 4 of them in Rio de Janeiro city and the last one in Seropédica city. The reason to include Seropédica is because Rio is a very large city and the four stations do not fully cover its area, put in the western region. So, including Seropédica station, we were able to better represent this region. While the inclination was varied, the solar chimney is also fixed to facing the north. The estimation of solar radiation on inclined surface was taken from the isotropic sky model of Liu and Jordan, which is represented by the equation below. As can be seen, this model considers the direct and diffuse radiation, which are estimated based on the global radiation provided by the database. This model also includes energy coming from the surroundings, the albedo. So, as mentioned before, this equation was used for each one of these measurements on 9 tilted conditions, resulting in a very large amount of data for the simulation of the chimney. This table also shows the location of the 5 weather stations and the amount of collected data, which are hourly measurements between July 18 and July 19. After handling the data and removing the night measurements, because solar energy in this interval is zero, and performing the simulation for the inclinations, we had approximately 200,000 of data to simulate the solar chimney. And the last column shows an average of the solar radiation at the midday. And again, some important equations to calculate the radiation on inclined surface. The extraterrestrial irradiation, used to calculate the direct and diffuse radiations based on the Erb's correlation. And the RB factor, a geometric factor used to calculate the direct radiation on an inclined surface. After simulating the solar chimney, we evaluated the results through the averages. This figure shows how small inclinations benefit the heating of the plate. The y-axis is the mean temperature reached by the absorber plates per hour. Between 10 and 40 degrees, the heating process is higher and the temperature reaches 350 kelvins. And as is higher the inclination, as lower the mean temperature. And the most relevant factor to this is the latitude of these cities. And now, looking for the glass temperature, the same behavior was found, but with small values, around 315 kelvins at the top, as we can see on this figure. At first, this would imply a higher temperature difference between the chimney wall and the air, thus providing a higher airflow. And then, when these temperature differences are plotted, it is possible to see that small inclinations are more effective to heat up the air, and therefore there is a larger variation between the air in the chimney and the air inside the room. For example, the 10-degree inclination increases the temperature by almost 12 degrees, while the chimney in the vertical position produces an air heating of 4 degrees. But not necessarily, a higher temperature will provide a higher airflow, since the airflow is also dependent on the vertical height between the inlet and the outlet, the stack height. This figure shows an average mass airflow, and as expected, it increased from the sunrise to noon and it decreased from noon until the sunset. The maximum value was 0.0138 kilograms per second at noon and 60 degrees of inclination. It is also possible to notice that when between 50 and 80, the airflow is almost the same. At noon, for example, the maximum airflow variation for those angles were less than 4%. However, for inclinations below 40 degrees, there is a considerable decrease in the airflow, so this range should not be applied in solar chimneys on these two cities. So in general, 60 degrees works better, but through the year, the solar energy intensity changes due to the seasons. So it was necessary to analyze the best chimney inclination along the year. This figure shows that the inclinations are similar to the presented before, with optimal values being achieved for angles between 50 and 70, depending on the month, and the maximum flow occurs on April. It appears to be wrong that April has the highest airflow, and the explanation for that is the influence by the zenith angle. A low zenith angle means that the sun is quite unvertical to the chimney, thereby reducing the solar radiation that reaches the absorber plate and consequently reducing the energy transferred to the air within the channel. In summer, the zenith angle is lower than in winter, so for higher inclinations, the chimney catches less energy. As an example, for 60 degrees, the solar radiation reaching the system is higher in April than in any summer month, resulting in the highest airflow. The chimney efficiency was also calculated. It is possible to see that the efficiency has almost the same behavior as the airflow. I mean that, increasing from sunrise until midday and then decreasing. The maximum average efficiency was 0.34 for 50 degrees, a little bit higher than the case for 60 degrees. In this figure, the average efficiency for each month are presented, and as can be verified, the higher efficiencies were obtained during the autumn and the winter seasons, since the average airflow also increases during these seasons, with the highest efficiency happening in April. As explained before, the main reason for that is the low zenith angle in the two cities during the summer. About the limitations of the study, we must notice three things. We have assumed the surface as smooth, neglecting the boundary layer effect. Many factors could change the value of the discharge coefficient, so for practical purpose, we have assumed a 0.6 value, and for less, there is a small heat loss through the glass by heat conduction, and this effect was also neglected. Suggestions for future works: we desire to expand to a CFD analysis and combine the chimney with other ventilation or cooling techniques. To conclude, the idea to use solar chimneys as an alternative ventilation method is plausible, but the airflow depends on its geometry and the solar energy. The best inclination for chimneys in Rio de Janeiro and Seropédica was a range between 60 and 70 degrees, and the stack height has much more influence on the airflow than the solar energy. And the next slide shows the reference for this project. Finally, I would like to thank Cefet for allowing the development of this work. And if you have any questions, you must write a comment below. Thank you so much. See ya.